After watching this video lecture, students will be able to define Gibbs free energy relative to reaction spontaneity, as well as calculate. Gibbs free energy, or delta G, is going to represent basically the amount of energy that's available in a system to do work. And Gibbs free energy interrelates our enthalpy changes and our entropy changes at a reaction occurring at a specific temperature. Okay? And basically, Gibbs free energy allows us to both relate the enthalpy and entropy of a system, as well as indicate the relative spontaneity of the process that we're observing. Okay, so we've already looked at spontaneity of a reaction relative to the change in the universe's entropy. Now, we've already looked at the entropy of the universe relative to the entropy associated with the system and the surroundings. So our equation, delta S of the universe, being equal to the delta S of the system plus the delta S of the surroundings, was something we discussed in previous lecture. And we know that the more positive our entropy value of the universe, the more spontaneous the process is going to be. Okay, and so we can actually analyze this delta S of the universe in a slightly different way by taking into account the fact that we know that delta S of our surroundings is equal to the negative delta H of our system divided by temperature. And we discussed that shortly in our previous lecture, but if we take this relationship here, we can subsequently connect our Gibbs free energy equation to our entropy equation that we've already discussed. Okay, so by plugging in our delta S of our surrounding variable, we can now get the following equation. Now, with the equation that we have here, we now see that the delta S of the universe is being defined relative to both system situations associated with the enthalpy and entropy values of that system. Okay, and if we actually take this another step and basically manipulate this equation by multiplying through with negative temperature, we continue this process and now get closer to interrelating these two equations. So if we're going to go ahead and do that, so if we take our negative temperature, we multiply everything through, what we end up with is the equation that we see here. Now, what I want to point out, guys, is that this portion of the equation resembles what we have here for Gibbs free energy. So basically what we can say at this point is that our negative T delta S of the universe is going to be equal to our Gibbs free energy. Okay, and so this interrelationship, as you can see, is going to be equal but opposite in sign. So a positive entropy change of the universe obviously is what we want in order for a system to be occurring spontaneously. In the case of Gibbs free energy, when the change in Gibbs free energy is greater than 0 or positive, it's non-spontaneous. Okay, and when Gibbs free energy is less than 0 or negative, it is spontaneous. Okay, so hopefully you guys can see how we have now interrelated our delta S of the universe to Gibbs free energy. Now, the nice thing about Gibbs free energy in this equation is that now we can directly just focus on the system alone. We don't have to worry about surroundings, and we can analyze from the perspective of heat exchange as well as entropy. Okay, so we're going to go ahead now and look at various ways to calculate Gibbs free energy. Now, just really quickly, before we look at the 3 ways to calculate Gibbs free energy, I want to review really quickly what standard state refers to. Basically, gases at standard state are going to be at 1 atm of pressure. Liquids and solids are going to be in their most stable form at a pressure of 1 atm and whatever temperature of interest is that we're analyzing from. We're usually looking at 25 degrees C or room temperature. And then solutions, things that are dissolved, are going to be in standard state when they have a 1 molar concentration. Okay, so just keep these things in mind as we progress through the next several slides. Okay, so above you guys see once again the Gibbs free energy equation. What I want you guys to notice here are the not symbols. The not symbols are recognizing that we're using data that's in its standard state. And so basically that's what the not is referring to. And the reaction portion here that we're seeing is referencing the specific reaction that we are analyzing the Gibbs free energy of. Okay, now there are three ways of calculating the change in Gibbs free energy of a reaction. The first being the use of tabulated enthalpy and entropy values. Okay, and these values are basically available in appendices, either provided or tabulated in the back of your book. Methodology 2 is once again using tabulated data, but in this case we're using Gibbs free energy of formation values from those appendices. And then the third step is basically a reaction summation approach, which is very similar to the Hess's law approach that we did in previous units. Okay, so we're going to first start with method number 1 and then go through the other two. So we're going to go ahead and look at methodology number 1 to calculate our delta G of reaction. Okay, so remember guys, we are going to be using both our enthalpy values that are provided in tabulated data form, as well as our entropy values that are also found in data tables. And we've already kind of explored a portion of this. We actually looked at calculating delta H values using the products minus reactants equation. We did this in the thermochem unit. So basically we're going to apply that same approach to both our enthalpy and entropy values. Okay, now something to keep in mind is that when we are doing these problems, guys, we want to make sure that the data that we are tabulating is being organized properly, as well as the units being analyzed properly. Okay, so I'm going to go ahead and set up the generic delta H of reaction calculation and delta S of reaction calculation for this reaction here using this tabulated data. And then on the next slide, we're going to plug these values in and calculate our delta G of reaction. So now that we have the generic equations, we're going to go ahead and utilize the tabulated data here. Plug in those values for our enthalpy of formation and our entropy at standard conditions, and then calculate our delta H naught of reaction and our delta S naught of reaction. Now that we've plugged in each of our values for our enthalpy and entropy respectively, we calculate these and get the following two answers. So now that we have this answer and this answer, we can take them and look at plugging them into the equation above. However, something I want to point out, guys, is the units. Notice kilojoules and joules. We cannot add together or subtract kilojoules and joules, so there will have to be a conversion before that can actually happen. So we're going to go ahead and do that on this next slide. Okay, so let's go ahead and work on plugging in our values to calculate our delta G of reaction. So again, guys, remember that the units here, they don't match. We have joules and kilojoules, so we want to make that adjustment respectively. I'm actually going to turn kilojoules into joules, although technically it does not matter. Just make sure that if the question itself asks for a specific unit, that you convert either or to the unit desired. Okay, another thing I want to point out is we have our temperature value here. On the previous slide, it told us that the reaction was being run at 25 degrees C. Notice that the units here for entropy change is in Kelvin. Okay, so we need to adjust this to be in Kelvin respectively. Okay, so I'm going to go ahead and set this up with all the appropriate adjustments. Okay, so now that we have our setup, I've plugged in my adjusted enthalpy value here. I've also plugged in my adjusted temperature value in Kelvin, and I've plugged in my entropy value here. Okay, so if I plug this into our calculator, we end up with negative 70.9 times 10 to the third joules. Okay, and so our delta G value here is going to be negative. Okay, so basically that negative sign indicates that this reaction at 25 degrees C is going to be spontaneous because a negative G value corresponds to a spontaneous process. Okay, so this is just the basic approach to this type of Gibbs free energy calculation. Now, something I want to point out, guys, is that we are able to use this equation at temperatures other than 25 degrees C. I know we're using standard state values, but the assumption here is that our enthalpy and our entropy are not going to change very drastically for the processes with temperature changes. So with that assumption in mind, we go ahead and we can use this equation at any temperature. So now let's go ahead and let's look at another way to approach delta G calculations. Okay, so very similar to what we just saw on the previous slide with our enthalpy and entropy values, we now have this equation which is going to relate our free energy change to the Gibbs free energy formation values that would be tabulated in a data set. So basically, we're going to approach this problem from the same perspective that we did the enthalpy and entropy calculations on the previous slide. Okay, so we're going to set up that generic outline. Okay, so now that we have our products minus reactants set up, we're going to plug that into our equation and go from there. Okay, so now we've plugged in all of our values from our chart down here, as well as the appropriate mole quantities from the balanced equation. Okay, and we plug this into our calculator, and that's going to give us a delta G value for this reaction equal to negative 148.3 kilojoules. Okay, so again, this process at 25 degrees C, because the sign of the delta G is negative, is going to be spontaneous. Now, something I want to point out, guys, is that this methodology is really only going to be useful at the 25 degrees C temperature value. Why? Because that's generally what our tabulated data is measured at. So this is a little less useful in terms of calculating your delta G at various temperatures, but you can utilize this at that specific temperature. So now let's go ahead and let's look at the third and final methodology for calculating our delta G naught. Okay, so this last methodology that we're going to be utilizing to calculate our delta G of reaction for this particular process is by taking known reactions and their delta G values and basically summing the equations to give you the overall balanced equation above, and subsequently summing the delta G values to give us the delta G associated with this reaction here. So it's basically like a Hess's law problem, except we're using Gibbs free energy values instead of enthalpy values. Okay, so if we go ahead and we kind of start analyzing this first reaction here, what I want you to do is I want you to look at your reactants and products. Okay, I want you to notice that the reactant here is actually a product on this side. So we know with this particular reaction, we're going to have to flip this equation in order to get the species on the appropriate side. Okay, so when we flip that, we end up with the following equation. Okay, now that we have this equation, we also know that we have a new delta G value for this process, and that's going to be positive 2074 kilojoules. Okay, so now that we have our product on the correct side, we now need to look at equation 2 and see if we need to make some adjustments there. Okay, so in this case, the only substance that we really care about here is the carbon, okay, because carbon is a reactant. However, I want you to notice that there are 3 carbons in the reaction above and there's only 1 here. So we know we need to take this equation here and multiply it by 3. And when we do that, we get the following equation. Okay, and so this equation is now going to have a new delta G value, and we're going to get that new value by tripling our original delta G that was provided, which is going to give us negative 1,183 kilojoules. Okay, and the last thing we need to do is look at our third equation here, and we need to figure out what side everything belongs on. So once again, we have hydrogen on the left-hand side. Hydrogen is actually a reactant, so this is the side we want it on. However, there are 2 hydrogens here, and we actually need 4. So we're going to actually multiply this equation by 2 in order to get the correct multiple. Okay, so now applying that, we're going to get the following. Okay, so now that we have this equation, we also have our new delta G value that's associated with it, which is going to be negative 914.2 kilojoules. Okay, and then what we're going to do is we're going to check and see which variables cancel and if these equations sum to our overall equation. Okay, so first of all, if we go ahead and we look at this, we have 3 CO2s on this side and 3 CO2s on that side of the arrow, so those cancel each other out. Okay, we got 4H2O and 4H2O. Okay, we also have 3, 4, 5O2 on this side and 5O2 on this side. Okay, and the things that remain, thus the following equation, which is the same equation as what we were wanting to solve for above. Now that we have obtained the correct equation, we know that we can take our delta G values and sum them. Okay, so if we basically add these all together, our delta G value for the process that we are looking at is going to have a value of negative 23 kilojoules. Okay, so again, this process that we're looking at here also has a negative sign. A negative sign corresponds to a spontaneous process. So this process is going to happen on its own. Okay, so this is just the third way to analyze this and do these types of problems. And now you know.